Great. So yeah, thanks a lot. Thanks a lot to everyone for being here, especially given how the day looks like. And thanks a lot to the organizers, Camilo, Laszlo, Vladimir, and Tristan for inviting me. Yeah, first of all, let me start, because otherwise some of them may get angry, that my research has been supported by NSF, the European starting, the European Research Council, and this Maria de Maeztu Award in Spain. So I'm going to talk mostly about some new work done in collaboration with Alex Ionescu from Princeton and Jaemin Park, who was a former student of Yao Yao at Georgia Tech, and he's now my postdoc in Barcelona, and unfortunately moving out to Switzerland from next year on. Okay, so both of them, Yao, and I see that Yao and Jaemin are online. So let me get started. Yeah, I guess in this context, for this audience, the SQG, or the surface quasi-geostrophic equation, doesn't need an introduction. There is a scalar theta driven by an incompressible velocity u. So then the relation between the velocity and the stream function, or between the scalar and the stream function, is given via this fractional Laplacian. And if we do that, then we can easily recover the velocity by means of a singular integral. Okay, so this is a singular integral. This, the R1 and R2 are the Riesz transforms. This is an operator of order 0. And these equations come originally from geophysics. So geophysicists were trying to use them to model like fronts of hot and cold air. They did many numerical simulations in the 40s and beyond. But it wasn't until the 90s when Konstantin Mayer and Tabak showed, first of all, local well-posedness in a Sobolev space. And on top of that, the analogy with 3D Euler. Okay, and this is because of this, the order of the singular integral operator. And there are some more strong analogies between SQG, which is a 2D problem, and 3D Euler. But yet, even in this case, we don't know if there is finite time blow up or global well-posedness. Okay, so that's still the main open question in this context, or for this problem. There have been some advances lately, but this is still a very difficult question. Okay, so if I were to compare with 2D Euler, and I abuse notation and I call the vorticity theta just to keep the equations the same way, then everything is the same, other than this relation between the scalar and the stream function. So now this is less singular. We have here a full Laplacian. We can still get a singular integral operator of order -1. Okay, so that's kind of the comparison between 2D Euler and the SQG. And moreover, we can think about a family interpolating between these 2 points, between these 2 laws via this fractional Laplacian, where we adopt the convention that for alpha equal to 0, we get Euler. For alpha equals to 1, we get SQG. But this is well defined all the way up to 2. Okay, so alpha here ranges from 0 to the open interval in 2. So there are some local existence results by Chaya, Konstantin, and Wu, and Chaya, Konstantin, Cordova, Cancedo, and Wu, depending on the range of alpha, and also some probabilistic results by Namot, Pavlovic, Stafilani, and Tots. Okay, so throughout this talk, I'm going to be focusing on patches, on the patch setting. So I'm going to assume that the scalar is a characteristic function of a set that is going to move with the fluid, is going to be transported, and this structure is going to be preserved for all time. So for 2D Euler, this is known as the vortex patch problem, and one upshot of this setting is that there is a closed equation for the boundary. So if I look at how the boundary moves in the normal direction, what is the normal velocity of the parameterization of this boundary, which I'm taking to be z, then I can write this velocity in terms of a singular integral acting on the parameterization of the boundary itself. So that's good because now our problem becomes 1D. So we have gone from having a 2D problem in principle to a 1D problem. And in this case, the question for many years, there was the question that even in this simpler setting, whether there would be global existence or let's say a finite time self-intersection, there was some numerics indicating one thing or another. And in the 90s, Jaemin and Bertozzi-Constantin proved that if your initial data is C1 gamma, then you stay in C1 gamma for all time. Okay, so that question was solved. And again, the date here being the 90s is going to be slightly important by when I show some of the pictures. So in a similar spirit, we can write the SQG patch problem or the generalized SQG patch problem by playing around with the power here. For SQG, this becomes 1, but you can imagine that you can get a similar equation for all values of alpha. And this is well defined, there's no problem with it. Okay, so Rodrigo in his thesis proved that this equation using a Nash-Moser argument is in C infinity locally if the initial data is infinity, and this was improved by Gancedo in his own thesis by proving the same if you start in H3. H3 is the Sobolev space, and there are some more improvement lately in lowering the regularity. Okay, how about singularities? Can one prove finite time singularities? I mean, I already said no, but or not yet. Let's try to be optimistic. But for example, one can rule out certain types of singularities. So Gancedo and Strain prove that there are no splash singularities. So the interface cannot self-intersect in a smooth way. That cannot happen. There is a very nice example by Kiselev, Rysik, Yao, and Slatos in the case where you have a boundary and you take, so this boundary, and you take two patches that touch the boundary, and then you see where do these points go because of the symmetry, they will stay symmetric. And you can prove that this point can reach the origin in finite time. So unless something bad happens before that, then there is going to be a finite time singularity, or like this point and this point are going to collapse here in finite time. Okay. And then there is another paper by Gancedo and Patel where they improve the range of exponents from this space, using the previous improvement on the local existence theory. Okay, now how about without boundaries? So this is different because there is the boundary, and the boundary sort of fixes this point, and this point cannot move upwards. So there have been some groups doing numerical simulations, and pretty much there are two different scenarios. So the first one is 15 years old, and it takes two patches and they roll onto each other and eventually collapse. And at the collapsing point, the curvature blows up. So this was done some years ago by Diego Córdoba, Marco Fontelos, Ana Mancho, and José Luis Rodrigo. And more recently, Dritschel and Scott, they took as an initial condition an ellipse. And this ellipse may develop a self-similar cascade of instabilities. I will show pictures taken from those papers just to see what I mean. Okay, so this is the scenario by Córdoba et al. So you take the two disks. These are different snapshots from different times. The simulation goes in this order. So they start rolling onto each other, they stretch, and then there is some point where they touch. And the point of touching, of course, there is another point here due to the symmetry. There is a corner, or there seems to be a corner formation. So that's one scenario. But of course, the difficulty here is that even numerically, you don't really control this point. So this point sort of starts turning around, and it's not clear where this is going to happen, as opposed to here, where this point was set and it was only moving along one line. Okay, so this is the difficulty to prove anything or even to simulate, because this point can freely move anywhere. So it's difficult to get an idea about where or when the blow up may happen. And this is a slightly different picture. This is for a fixed time, very close to the collapse. And this is showing throughout scale. So every time you move on to the next picture, there is a magnification factor of 10 or 20, I don't remember, but it's on the scale of 10. So you start with 2 ellipses. Again, you see a similar thing. The ellipse rolls, stretches, and then it looks sort of like this, where you have like 2 blobs connected by a small passage. And then if you zoom in, you get this little structure. You keep zooming in, you get another structure, and so on, and so on, and so on, and so on. Okay, and this is about where the calculation stops, but it's remarkable that they can go 1, 2, 3, 4, 5, 6, 7 scales. Okay, so it's pretty compelling, but yet no proof.
What are the times? I mean,
no, this is for a fixed time.
This is for a fixed time.
This is for a fixed time. This is just zooming in space. So you freeze the time as close to the singularity as you can. I mean, you see it's not touching, but you have to zoom in like a factor of 10 to the 7 in order to see whether you're really touching or not. Okay, so this is as close as they could get to the singularity, but they were showing this phenomenon throughout a lot of scales. Okay, so computationally, this is quite a challenge, and there are many tricks and many good ideas to be done in order to really implement this carefully. And of course, this is like 10 years after the previous simulation, so there have been also improvements in the hardware and in the software in between. Okay, so today I'm not going to prove anything about singularities, and I'm going to try to go in the opposite direction. So I'm trying to say something about the global existence of solutions. Well, the first thing I can say is if you take a disk, then this is going to be stationary, and this is a very simple calculation that one can do. So these are stationary solutions for 2D Euler, SQG, modified SQG, and everything in that family. If you take an ellipse, then this is not stationary, but this is steady for 2D Euler. So if you substitute the ellipse into Euler's equation, then you get what is called now a V state, or a rotating patch with uniform rotating velocity proportional to some formula depending on the semi-axis. So A and B are the shortest and longest length of the semi-axis. And this is the angular velocity. And this just keeps rotating on and on forever. So that's another class of solutions for which you have global existence in a very particular way. But this doesn't go through for SQG or any element in that family. Okay, so back in time, 1978, keep in mind that the question of whether there were finite time singularities for the vortex patch was still open. So Dim and Sabuski started to do numerical simulations, and they were trying to find non-trivial solutions in the same spirit as the ellipses, but this time with 3-fold symmetry, 4-fold symmetry, and so on. And also keep in mind the technical resources from that time. So what they did was they started with the disk, and then they were able to show bifurcations from the disk at certain angular velocities, depending on the symmetry class that you're working on. And then by following that branch, then you get this sort of triangular shapes, which are neither a disk nor an ellipse nor something. I mean, these are like potato-shaped blobs, and yet these are solutions that exist globally because they are going to rotate uniformly. Okay, so these are numerical examples of a class of global solutions for the vortex patch problem. And again, of course, now they may not seem as interesting as before, but back then this global existence problem was still open. Okay, now this is a more complicated bifurcation diagram done by Cam in his thesis about 10 years after. This horizontal branch represents, so the horizontal axis is the angular velocity, and this branch represents the disks. This another branch represents the ellipses, and these M3 are the threefold and the fourfold, and there are many other branches here that he didn't calculate, but what he saw was that there were secondary bifurcations in the elliptical branch. So it's not just that you have these things emanating from the disk, but the panorama is much richer because you can even calculate or find numerically more complicated solutions bifurcating from these branches, not just from this branch. Okay, so this is just numerics, but yet it's saying that okay, there is a class of like a big class or a reasonably big class of non-trivial rotating solutions for 2D orbit. Okay, now what can we prove? So Burbia in '82 did the local bifurcation theory, and he was able to prove that if you start at certain angular velocities, then you can do the bifurcation and you can produce non-trivial rotating solutions. And the regularity of the boundary was improved to C infinity by Midi, Mateu, and Berbera in 2013. And we improved it to be actually analytic, and we computed the secondary bifurcations that, I mean, we proved the existence of the secondary bifurcations that you were seeing in the previous picture.
How do they look like?
The
secondary one.
You perturb, well, they all look like potatoes to me. I mean, it's taken a list and
okay, I don't know where you're buying your potatoes, but
maybe not the triangular one, but you take an ellipse and you deform it a little.
So they're all convex.
You can go into non-convex as well.
You can go into non-convex.
Yes.
But then the deformation starts being
right. But if you follow the branch, I mean, of course, when you bifurcate, you stay convex. But if you follow the branch, in some cases, you can become non-convex.
Is this only numerics or you?
No, this is numerics. But the numerics look pretty compelling. But of course, if you do like this, all of this is perturbative. So
yeah. I mean, it might be difficult to prove something qualitative.
Well, Hassaini, Masmoudi, and Wheeler proved global bifurcation. So these three results are local, and they were able to continue the branch until something goes bad, and they have some alternatives as to what can go wrong. And the result is of that sort. So the solution and the branch stays globally until something goes wrong, and there are a couple of alternatives, and they rule out some and they keep out some, and that's what they can prove. So we did sort of a similar program in this case, in the case of a smooth case, the singularizing a patch, and also other than these works, there are lots of people working on this problem, and I apologize if I don't cite everyone properly, but my point here is that this is quite active, and there are lots of people working on these kind of problems right now. Okay, what about SQG? Because right now we know that for Euler, maybe the global existence question is not so appealing anymore, but for SQG and generalized SQG, we were able to prove a similar statement. So we were able to show that close to the circle, we could find C infinity solutions, convex, n-fold symmetric, that are V states for the SQG patch. And then, okay, the angular velocity is given by some complicated formula involving gamma functions, but one can calculate it. And we were able to upgrade the C infinity regularity to analytic. So both these results use bifurcation theory in the spirit of the Crandall-Rabinovich theorem, and they are local bifurcation theory results. And here the difficulty is to design a space where the linear and the nonlinear functional go, and the linear function loses a logarithmic derivative, so one has to design carefully a space that does lose a logarithmic derivative, which is fine and not difficult, but at the same time fits well in the nonlinear framework. Okay, so this is something that we did a couple of years ago, and we were able also to deal with the smooth case. So we were able to produce a non-trivial global smooth solution that had finite energy. So now every level set was rotating with constant angular velocity. The solution was C2, threefold, compactly supported, and the initial data was close to a radial function. This is a kind of a cartoon. We were taking a profile in radial coordinates that sort of looked like this. It was smooth. And then we were bifurcating from this radial function. Before us, Dritschel had constructed rotating solutions that were not smooth, and after us, other people constructed other sorts of global solutions, like traveling solution or K-vortex solutions, and so on. Okay, so when I was presenting these things, sometimes I got the following complaint, like, okay, that's fine, that's quite interesting, but these solutions look very special. You're dealing with essentially like one-dimensional spaces or two-dimensional spaces of solutions. It would be interesting to know what happens generically. Okay, and you can pay the price of taking small data. Okay, so that's the game.
What a small mean.
Okay, I'll get into that. Depending on the setting, it's going to be one thing or another. Okay, so that was the challenge, and we didn't know how to. Of course, we didn't know at first how to prove like anything sort of generic. So this is where we started. So this is the first result that we did, and in that case, this is going to Vlad's question. We were working on the setting. Now the patch was not closed, but the patch was sort of open, and was a perturbation of the half plane. Okay, so now the patch. So the half plane is a stationary solution, and the patch that we were taking was open, and it was a perturbation of that. So in those coordinates, one can write the equation for the evolution of the patch. This is how it looks like, and Z again is the parameterization, and again alpha close to 0 is to the Euler, alpha 1 is the SQG. And what can
seeing the screen? We don't see the screen right now because we see you. Okay, thank you.
Is it good now?
It was fixed. Thank you.
Okay. Okay, so if we take the parameterization x, h of x, and I think of h as being small, this is going back to your question, then now this becomes a scalar equation just on x, and this is how it looks like. So there are issues here depending on alpha, and they are at infinity. So if alpha is too small, then this integral is not going to converge. At 0, like when y is equal to x, this is fine because there are enough cancellations. But at infinity, there are problems. So we took alpha to be bigger than 1 in order to ensure that this thing was well defined. Okay. So now our setting is going to be just like this. We're going to take alpha bigger than 1, and we're going to see what we can do. So roughly, just to get a feeling of how this looks like, if one linearizes, then DTH, this term goes away, and you end up with some form of lambda, or lambda to the alpha, if you want to write it like that. So there is some dispersive multiplier. I remove all the constants, but essentially, you have a dispersive equation with this kind of multiplier. Okay, so let's try to use that to our advantage. Let's try to use that we are in this flat at infinity setting, and we have like an infinite space to use the dispersion to our advantage. So this is what we proved together with Diego and Alex Ionescu. So we took alpha between 1 and 2. We took a bunch of derivatives. Then we can find an epsilon bar that depends on alpha only, such that any initial data which is small in this sense leads to a global solution. Okay, so this is a generic small data result for global existence in this framework, in this setting. And then after our paper, Hunter, Xu, and Zhang proved a similar theorem using the exact same proof in the case and for a different regularized version of the equation in the case alpha smaller or equal than 1. So the main arguments or the main ideas in this proof is to use the vector field method of Kleinerman, analyze the space-time resonances, and do a bootstrap argument. So I'm going to say a few words about how the whole thing closes and works out. So if we take alpha in this setting, again, the same parameters as before, we think of epsilon 1 as being small, but not too small, and epsilon naught as being really tiny. P naught is super tiny, and we take V to be the free flow by just the linear flow. Then if for some capital T, we have this estimate, so it's small but not too small, and initially we were very small, then we are actually very small here in between 0 and capital T. So we are sort of improving on, remember, epsilon 1 is small but bigger than epsilon naught. Okay, and here we are using this Z norm defined in this way. Okay, everything is uniform in alpha, there is no problem. The only thing is that the integral just doesn't converge if alpha goes to 1. But from the point of view of the scheme of the proof, everything goes through.
What's capital lambda?
This is the multiplier.
Okay.
It's whatever you get from the linear evolution. Lambda, yeah, I'm abusing notation a little. This lambda is not the standard square root of the Laplacian, but it is just what you get from the linear dispersion. Okay, so we want to do energy estimates, and to do that, I'm explaining this because it will become important later on in a different setting. So we can split our operator in 3 parts. Lambda, now this is back to your question, lambda is this dispersion relation. So we're going to get the linear term, then the cubic, so T is some paradifferential operator, sigma is some symbol of order alpha, quadratic in H, so this whole thing is cubic, and E is cubic and semilinear. Okay, so we're going to split it like this at first. And if we do that, then there is a problem if we want to do energy estimates because of this part. And alpha, remember, alpha is bigger than 1. So there is an I. So I T sigma. So then these 2 terms are going to work well if we try to do any sort of energy estimates, but this is going to work badly because this is not going to be imaginary. So that's a problem. So we're going to change variables in the spirit of the good unknown of Alignac, and instead of looking at H, we look at some H star, which is some reparametrization of H. Gancedo and Cordova did something similar or something very closely related using a different way, using a different reparametrization, not involving pseudo-differential operators, but it's almost equivalent, or at least it's equivalent to a higher order. So we can choose this B in a way that now our equation looks good. So we remove this part, and everything looks nice to be able to do energy estimates and cubic and semilinear. Okay, and by doing that and doing then the energy estimates, and using this pointwise estimate, we can close. Okay, so that's one ingredient, and we'll get to see what happens about this later on. Okay, we also have to do dispersive analysis of this term involving the Z norm, and this is where the resonances come into play. If we look at the main contribution of this norm, then this comes from this cubic part. There is some phase, M1 is some suitable multiplier, and if we try to do stationary phase, integrate by parts, and so on, then we barely fail to get the good decay. We have some decay which is 1/t. If we try to integrate in t, we fail. We have a logarithmic loss, but we're almost there. So that would lead to just almost global existence, but we can get away by choosing a nonlinear correction to the phase. This is similar to what Ionescu and Pusatelli did for water waves. And if we do that and we choose this correction to the phase, which is has the right imaginary versus real part, then we can get modified scattering, and we can improve on the decay and not have to worry about the space-time resonances. Okay, so let me see how many time. Oh, perfect. So what about the compact case? I mean, this is a little bit like cheating, right? I'm using infinity. I'm changing the problem to make use of infinity and to make use that things disperse at infinity, and I'm using that heavily to my advantage. Okay, so the first thing is that, I mean, the first trivial observation is something like this is not going to work, because if I take a disk and I excite it with some wave, then it will come back. So I'm not going to gain advantage of that in the same way as I was gaining here, because things were dispersing in a different way towards infinity. Okay, so that's a problem. Let's see how we can solve it, or how we can do something about it. Okay, so by then, we were, this is how all these things start. We did some numerics, and just before I started, this is not the video that much. Okay, so the coordinates here, this is in radial coordinates. So one, this is the angle. One is the radius. So if the function were constant, then this would be a disk. So this is a small perturbation of a disk, just I don't know, like a random perturbation of the disk. And we start with this initial data, see what happens. This is of size epsilon, and we were simulating over scales of size 1/epsilon squared, so that we were hoping that maybe something would happen. And I mean, it's nice, it's interesting, but nothing really seems to happen, in the sense that there is no dramatic growth, nothing that would suggest that the singularity is forming. This is done for alpha equal to 1.5. We tried different exponents, we tried different initial conditions, and okay, it looked like this hypnotic, I don't know, curve moving on. It just doesn't grow. I mean, it's stable, but there is not much that you can do. And then we thought, well, maybe this is because we're simulating over two shorter scales. So let's try now with a scale which is epsilon cube, and this is accelerated, and you still see kind of the same thing happening on and on. Nothing really, I don't know, too dramatic going on. So if we were looking for singularities, then that's bad news. But if we are looking for some form of global existence, then there is hope, because we try. I mean, I'm showing here one realization, but we tried with several initial conditions, and they all sort of look the same in that sense. So, okay, This thing is definitely not periodic. So this thing is definitely not periodic, but we thought, well, maybe this is a quasi-periodic solution. And indeed, this is what we can prove. So this is joint work with Alex Ionescu and Jaemin Park, and hopefully the paper will be out in a week or two. So this is somehow a slightly watered down version of the actual statement. This is the following. So take your favorite exponent in 1, 2, fix it. You can take any exponent that you want. Now take a set of modes under some genericity conditions. There are some things that are forbidden, but there are not many forbidden configurations. So you fix your exponent, you fix your equation, you fix your set of modes. Then there exists an epsilon or an epsilon naught such that for any epsilon between 0 and epsilon naught, one can find a Cantor set of frequencies such that for any frequency in that Cantor set, there is a quasi-periodic solution of the modified SQG for this alpha, okay? And that solution is epsilon away from the disk, plus maybe some smaller terms. And this epsilon away piece is supported in the set of modes given by the set of modes that you chose a priori. So essentially you can excite any or almost any set of modes for any equation in this range, and you can find a quasi-periodic solution. The solution is linearly stable, and this set C epsilon has full measure. So pretty much you can realize any frequency as epsilon goes to 0. So the set of frequencies that you can realize versus the total set of frequencies goes to 1.
Sorry, what do you mean by Cantor-like?
You take all the frequencies and you take out a bunch of them.
The complement of the Cantor-like set.
Yeah.
Okay.
Yes. Yeah. Okay.
I mean,
sure.
Cantor-like set is kind of the exception.
Okay. No, then it's everything but the exceptional one.
Yeah. Can you say more about the set S? Can it be very small?
Yes. You can take S to have one.
Only one.
Nu can be taken to be 1.
Okay. There is no spilling out at all.
No, I mean, there is some spilling, but the majority of the mass will be concentrated.
Oh.
I'm not claiming that everything is supported in set. Is the majority of the mass is supported on the set. There is spilling indeed, but this spilling is to a lower order.
Okay, thank you.
The frequency vector is just like a 2-dimensional vector?
It's a new dimensional vector.
No, the C is in the same lattice?
The C, which this?
The Cantor set. Oh yeah, it's living inside of S?
It's living inside of R to the N.
It's an R.
Can you say anything more about the C epsilon? Like, I don't know,
yes.
dimension small.
It will go to have full measure. We can get estimates on the measure depending on epsilon. As
full measure as epsilon goes
right.
to 0.
Right.
I mean, like the complement is still kind of possibly thick, like a small positive measure.
But as epsilon goes to 0, the complement, the measure of the complement goes faster than the measure of the whole thing.
Yeah, understand.
Yes. So we can get bounds on the measure of the exceptional set or the good set for that matter. Okay, so some remarks. As I said, there are no external parameters. We get what we get. The equation is what we get. I mean, once we select alpha, there is no more choice. So there is no other possibility or any trick that one can play to make your life easier. There is no restriction on alpha other than alpha being greater than 1. So this technically is more complicated because we cannot get a result that relies on, let's say, for almost all values of the parameter or use that in some way to our advantage. There are lots of calculations the equation is quite singular in this regime, so we need to do expansions to a high order. There are some recent results in this setting, in this direction. So Hassainia, Midi, and Masmoudi in October of 2021, they proved a similar result for almost all values of the parameter in this range. So they use alpha as a parameter, and that way there are, like, some of the estimates get easier, but yet it's also quite a technical feat, and this is what they prove. So they can do it in the less singular range. Then Berti, Hassainia, and Masmoudi, well, 2 months ago, they were able to prove that for the vortex patch problem, close to almost all ellipses, so they are using the aspect ratio of the ellipses as an external parameter, they can find these solutions. So in the CAM thesis, one could see periodic solutions close to the ellipses, but these are quasi-periodic solutions close to almost all ellipses.
Is that for 2D Euler? Or?
Yes, okay. This is for 2D Euler, and this is for 2D Euler as well. Yes, yeah, but just to link it with the picture that I showed, there was the elliptical branch, and there were some crossings there corresponding to periodic solutions. But then for almost all, possibly for all values of the aspect ratio of the ellipse, then there are these quasi-periodic solutions. And also two months ago, if you work in the setting where you are confined to a disk, and you take now some patch here, this is again 2D Euler, and you play, now you don't have the dilation scaling anymore, and you play with the radius of the small disk, and you use it also as an external parameter, then you can prove that for almost all disks, for almost all radii of disks contained within a disk for 2D Euler, then you can find also quasi-periodic solution. Okay, so in these 3 papers, there is some help by the relaxation of the condition of for almost all values of the parameter, whatever that means in this context. Whereas here, we don't have that luxury anymore. Okay, so we rely on the ongoing work done by Berti and his collaborators and his students for the last 10 years or more. So I mean, I remember when I arrived, Berti came, gave a talk, and I was pretty impressed by the sort of things that they were doing and what they have been doing from then on. So they started with 80, quasi-linearly force 80, and then these are all results of the same flavor. So construction of quasi-periodic solutions close to 0 or close to some particular solutions. So they started with 80 and later did KDV and MKDV. But in a couple of years, they were able to move on to water waves. So they were able to prove similar results for gravity capillary water waves using surface tension as a parameter. And then for the gravity case, infinite depth, and using the depth as a parameter. There is also the work of Baldi and Montalto where they do force 3D Euler. And also some recent work of Feola and Giuliani, where they do the gravity case, infinitely deep, but in this setting without parameters. Okay, so this is what has been going on for the last 10 years or so in this community, and this has advanced pretty rapidly. I mean, all of these papers are really a tour de force in technical power. Yeah, they are like, all of them are over 100 pages. So it's pretty tough. Okay, so now let me say a few words about the proof. Let me start. I mean, we cannot write the equations in a simpler way, as I showed before, for the different settings, because we have to recast everything use the Hamiltonian structure of the equation and recast everything in Hamiltonian variables. So if we look at the Hamiltonian, which is the integral of the stream function, and if we write it in radial coordinates, so now this R is going to be the parameterization of our patch, then the nice variable to have is not to parameterize the boundary, so R of alpha, if we take the partial, so the boundary as being parameterized by R of alpha, cosine of alpha, sine of alpha, then it is not good to write R as 1 plus F, because that will not respect the Hamiltonian structure of the equations, but instead as the square root of 1 plus F. And by doing that, then F satisfies this Hamiltonian equation. So now our patch, we can think of F as being very small. So if F is 0, F is the disk. And we have to work with the evolution of this F. Okay, now you can imagine that by substituting this into the equation, then it becomes awful. So there are lots of terms, and there is nothing you can do about it. If you want to use this Hamiltonian framework, then this is the variable you have to take, and you don't have any other way. Okay, so if we were to expand the Hamiltonian to first order, so the quadratic part of the Hamiltonian leading to the linear part of the equation, then we have, okay, it's not so bad. I mean, it looks awful, but if you see like H3, H4, and H5, then this is fantastic. Because here you can do the calculations in like 10 minutes and by hand, and everything is not terrible. Later on, then you really struggle. So this is how the thing looks like. There is some nasty multiplier at the level of alpha derivatives, or lambda to the alpha partial x. And there is another one at the level of partial x. So morally, if we were to expand close to the disk, then this is how it looks like for the different modes. There is some dispersive multiplier and some nonlinearity. Okay, so the philosophy here is to say, well, this is our nice dispersive multiplier, and we are trying to, and of course, this is just for H2, there are like the rest of the nonlinearities. So we're trying to bifurcate and upgrade these linear solutions that we can construct from here to preserve them at the nonlinear level. Okay, so a slightly different point of view is the following. Let's try to write everything in action angle coordinates. So if we split our function into the modes that are supported in S and the modes that are not supported in S, and we decompose the coefficients in this way, and we look again at the linear piece or the quadratic part of the Hamiltonian from 0, then there is a trivial invariant torus, namely whenever the y's are 0 and the z's are 0. The z's is the part that spills over. So now what we want to do is to upgrade the embedding or the parameterization of that invariant torus, which is the trivial one, into the nonlinear framework. Okay, so effectively what we want to find is a 0 of this equation here. And here this H epsilon is the rescale version, taking now into account of the Hamiltonian, taking now into account the different sizes. So this also goes back to the previous question by Peter. So Xi is going to be epsilon square. This whole thing is going to be of size epsilon because the y's are going to be lower order and the z's are also going to be lower order. So there is some spilling into the normal modes, but the main part is going to be given by these v's. Okay, so also related to these Cantor sets and what is like the c's and so on, one can identify under some non-degeneracy conditions the set of amplitudes, which are the set of x's, and the set of frequencies, and essentially they are one-to-one. So if you tell me what the amplitudes are, I can figure out what are the frequencies and so on. Okay, so now proving things for most frequencies is going to be the same as proving things for most amplitudes. Okay, so the main goal is to prove that we can find a solution for almost all elements in this set. Okay, so this is how it's going to work. We're going to run a Nash-Moser argument on F to find solutions. So we need to understand really df, not just at 0, but at every point. We need to linearize df at any approximate invariant torus that we find along the Nash-Moser iteration, and then understand this linear operator and try to say something about the inverse. So this is going to lead to non-constant coefficient operators, which is a pain, because we have to invert some operator that doesn't have non-constant coefficients. It's enough to construct an approximate inverse, meaning an inverse that is exact at a solution, but not totally exact whenever we are not at a solution. And it is also enough to focus on the normal direction part of the df. So whenever this df is the derivative with respect to the normal modes. So the way we are going to deal with this is starting from this non-constant coefficient operator. We're going to try to diagonalize this operator by applying symplectic transformations. So ideally, we would like to transform our linear operator into a constant coefficient operator. That would be fantastic. We cannot do that, but it's enough to do it up to semi-linear reminders and very little terms. And this O of epsilon squared is a pain, and this is a byproduct of having to deal with no freedom in the parameters. So if we were to take almost all alphas, then this requirement would disappear and our life would be a lot easier. Okay, so this is how the linear operator looks like. We have omega partial phi h, some main term and some remainder. So the main term, we can write it in this way. There is some piece of it, which is, remember there is a dx outside. So there is some piece of it, which is at the level of alpha minus 1 derivatives via this integral. Some piece of it, which is at the level of 1 derivative, and some piece of it, which is at the level of alpha minus 3 derivatives, okay? You can say, and then this is, at this point, well, cheating a little bit, this is nice, or almost nice. So the plan is to deal with M and reduce each coefficient of M to be constant, or to put it into some remainder where it is small enough and semi-linear. So a priori, the problem is if we don't do really anything, this may be too big, because there are certain interactions between the V's and the Z's that lead to terms that are just too big. So we need to first do a normal form to remove some of the interactions between the V's and the C's that appear in the R. Okay, so that's step one, and I'm not going to detail it here, but there is this step to be done. Okay, then one thing we can do is to reparameterize space. So if we conjugate the operator that we had before, then we can conjugate it in a way that now we remove the x dependence of the top order. And we do so by conjugating with this change of variables in space for a suitable beta. And just to get a feeling of how we can gain is if we compose with A from the right, we compose with A inverse from the left, then we are left, and okay, we pretend that this is not a nasty integral operator, but just a simple derivative, then we would get something of this sort, and we would be able to choose the right beta in order to make this coefficient here independent of x. Okay, so that's the first step. The next step is to make the B1 that I wrote before independent of phi. And we change again variables and we reparameterize time. So by reparameterizing time and setting the right change of variables, we can make the coefficient in front of this guy and the coefficient in front of this guy to be the same, so that we can later divide by that factor and make it purely constant, independent of anything. I mean, independent of omega, but dependent of omega, but independent of phi or x. So now our operator is constant to top order, and then, okay, then who knows what happens after. Okay, so let's keep moving. Then we do, we are trying now to kill this guy, and for that matters, all of them. So we're going to use a conjugation by the one flow of this pseudo PDE for suitable A's and suitable beta. We will choose the beta, like if we think about what is this, then, and we sort of do the Duhamel formula and we expand, then we're going to get A's and commutators of A's with these things, like with what we have in the linear part, like in the linear operator. So by choosing beta carefully, we can produce a commutator between the A and the top order that somehow is split at the level of the second highest. So if we do that, then that's great, because we can choose the A in a way that the contribution from the C2 and whatever this commutator gives to be zero or to be constant. So that's fantastic. We have dealt now with the operator, or with the part of operator at order 1, but the problem is if one of these commutators appears, then there are going to be a lot of them. So if there was a commutator between the change of variables and this guy here, in order to overcome this one, then we're going to have, like, when I look at the second commutator, it's going to be at alpha minus 2 times alpha minus 1. So you can think that if we produce something to interact with this one and make this one constant, then by applying, I mean, this is going to be an infinite series. So it will spill over up to here. And so on. So it will create lots of terms arising from what we created in order to simplify this one. So now, if alpha is large, like 3/2, then this is not so bad, because we create something at 1/2 and then we end up being semi-linear. But if alpha is very close to 1, this leads to lots and lots of terms that we have to control. So eventually this stops, but we have to do 1 over alpha minus 1 times this thing, because if we create this new one from canceling this one, then we need to do this thing again with this separation, and again it creates more and more terms. So you can imagine that that this is quite involved in order to be able to sort of make all this thing work. So at the step K, we can cancel this coefficient, but we're going to create new coefficients at any other power of this form for L bigger than K. So it's quite delicate to keep track of everything. And this is in fact one place where the proof breaks down if we were to take alpha is equal to 1. So if alpha is equal to 1, then we don't have 1 and 1. We have essentially 1 and 1 plus log. So that at every step of this method, we would just gain a log. And then there is no way to go to semi-linear by doing these kind of iterations, and we would have to perform these things an infinite amount of times, and then we don't know how to control like the infinite series.
By stops here, you don't mean that you cancel out everything.
Finite.
I mean, you said that you need to do this algorithm some number of times.
Yes.
And after this number of times, you have just higher order terms, which is very small, and you don't care about them. It's not like you cancel out everything.
No, I mean, once I go to semilinear, then I'm good.
Okay.
But I'm not canceling the whole expansion. So yeah, as long as I'm semilinear, then life is good. But if alpha goes to 1, then I'm taking only smaller and smaller steps. So I need to take more and more steps of this iteration. Okay, and so things look good at this point. We are constant coefficients plus semilinear, but we haven't really dealt with these smallest conditions of order epsilon squared. Now, if we were to use alpha as a parameter, then most of these steps can be avoided. The normal form that I mentioned before, or the linear Birkhoff normal form that I am going to discuss just now. So in order to remove these terms, the terms that are big O of epsilon and big O of epsilon squared, now that we are constant in the things that we like, we can conjugate with respect to this operator, where A1 is smoothing. And then by doing so, we can remove the terms that are big O of epsilon. But we create things that are big O of epsilon squared. So we have to do another pass with respect to a different operator for another A2 to remove these terms which are big O of epsilon squared. And then, okay, after doing all that, then the whole thing goes through. We can do the Nash-Moser, we can apply KAM theory and construct this Cantor set of good frequencies or good amplitudes where we can find the non-trivial embedding of the torus. So let me stop here. Sorry, I went over time.
Well, you started late. Questions?
So in principle, these numerical simulations, if you run them for a sufficiently long time on a generic solution, they could slowly migrate to these higher modes, right? These are like these stories which could be exceptional, and the generic solution could still, like if you run it for a million years.
Yeah, in principle, but if you run it for a million years, then you have so much errors that you won't be able to.
Would it be realistic kind of numerically to check if you have some minuscule leakage on a generic solution?
Yeah, I mean, we didn't try it. We were already, I don't know, scratching our heads when like we went from 1 over epsilon squared time to 1 over epsilon cube time, but we didn't try to monitor like the leaking, or I mean, it was already quite compelling that we didn't see the thing growing too much, even for a very long time. So then we stopped doing numerics and we started doing estimates.
It seems you have a lot of these stories.
Yes. Yes.
What's in you said there was a forbidden set of modes. Like, do you know what's in there? Or?
Yeah. We need to have some estimates on the frequency related to resonance conditions.
Okay.
So that's what we are excluding. Otherwise, it's complicated to invert the, like we don't know how to get like good estimates on the inverse of the DF.
And do you think bad things happen in that set of modes? Okay.
There could be resonances there, and bad things could potentially happen. Yes. Yeah. I mean, in the case of water waves, this is where you have like this, I don't know, Wilton ripples or other sorts of like resonant scenarios. So I would imagine something like this happening here.
And do you not have like the typical Diophantine condition on the frequency vector?
Mm-hmm.
Okay.
Yeah, I didn't show it because, but yeah.
How sensible is this? I mean, is the proof on the fact that you do it on the circle? I mean, is it conceivable that you can do it on some other or
Like on a manifold or
on some other stationary solutions.
but we don't know any issues.
Okay.
It is using that is dimension 1. This is heavily used. Yeah, we don't know how to do it on something which is higher D yet. But yeah, I mean, you need to have like the base object. This is why for Euler they could do it with effort close to the ellipses. But yeah, but the basis object here, like we don't know anything other than the disk.
I mean, would you expect there's a rigidity theorem which is telling you there's only the disk, or?
We've proved the rigidity theorem as well. But this is done with Jaemin and Yao.
Okay. So that's the only
for stationary solutions and rotating solutions in some ranges.
Okay.
So that's I mean, I didn't talk about it here, but there is some form of rigidity theorem.
Yes.
You can imagine small perturbations of a rotating solution.
Yeah.
Avi, in the Euler case, and I don't know necessarily others, you can have a far field perturbation that, in other words, you can have a step function on 2 circles or even 2 ellipses. Okay. So, and here, can you have a 2-step on 2 circles?
Yes. When it comes to constructing these sort of solutions, yes, that is the analog of the co-rotating vortex pair.
Right. So then can you destabilize if you can put a very, very shallow second step very far with the second circle very, very far and put a little bump on the original circle, the one for which you have just a simple linear to prove, I suspect that in the case of Euler, you can create needles and destabilize. So this is in the direction of instability or even blow up, but can you look at it a little bit in terms of modes if you put 2 of them?
Yeah, I mean, okay, we haven't done it, but I would presume that the situation is the same as with Euler. In that sense, it shouldn't be very different. So yeah, the honest answer is, I mean, I hadn't even thought about this problem, but like what you're suggesting, but I think it can possibly be done, yes.
It'd be interesting to have some instability results because of that.
Thank you, Peter.
Okay, there does not seem to be any more questions, so we start again at 10:30.